Hi, my name is Brandon Miles.
I'm Leslie Manning,
Luke Welch.
Tyler McKinney.
and this is going to be our design review presentation on pump storage. Alright, so let's go over the background for this project. So, most energy grids operate on the assumption of meeting demand as it's needed. They must anticipate demand fluctuations ahead of time in order not to over or under produce energy. The additions of intermittent energy to the grid complexify this challenge further. Surplus energy storage enables increased grid flexibility, stability, efficiency, cost reductions, and profitability. So, intermittent renewables will benefit greatly from the addition of energy storage solutions.
Alright, so gravity batteries are a type of energy storage technology that leverages the force of gravity to store and release energy. These systems are particularly suited for grid-scale applications and are gaining lots of attention as sustainable and cost-effective solutions for renewable energy storage. During low electricity demand periods, surplus energy from the grid, particularly intermittent renewable sources, are abundant. This surplus energy powers the system to lift heavy masses of water from our lower reservoir to our upper reservoir, storing it as gravitational potential energy. During the high demand periods, the system releases the stored gravitational potential energy, by allowing the elevated water to flow down through the system through our turbine, giving the energy back to the grid, producing a supply for our grid. Alright, so now I'll be going over the advantages of the pumped hydropower storage guide. And so first we're going to start with it's an efficient means of large-scale energy storage. It's got very quick response time in case of blackouts, spinning reserves for grid stability, and it's got frequency regulation. Alright, the system has a very long life cycle capability, upwards of 50 years. This is depending on the maintenance that is required, whether it be reactive maintenance for a part that fails in the system or preventative maintenance where we know the part is going to fail and we just want to replace it. And another key feature about this that we have to take into account is weather. You never know if the water is going to be at a higher temperature or a lower temperature. That will affect the motor, absolutely, and the piping and the control valve. So that is always a factor. Also, the longer the life cycle equals the better economics. It's less of a startup cost, it's less maintenance, the better lifespan it has. Modern systems can achieve around an efficiency of up to 80%. Also, compared to other systems, this is a very relatively low carbon footprint and less emissions and greenhouse gas that are produced compared to other systems. This can also support water management needs, either in a natural disaster such as floods or just preventative irrigation and heavy rain. Alright, so now I'll be discussing the disadvantages of the pumped hydropower storage guide. So first and foremost, there is a massive upfront cost with this because we have to get the land for this, we have to get the reservoir, we have to get permits, everything, we have to do tunneling, excavating. It's a huge upfront cost, so it's a really big play. Geographical limitations. So you have to have an upper reservoir and a lower reservoir, and we also have to have the incline down. So an example for Ontario would be the Niagara Escarpment, where there's a great disparity from the upper to the lower reservoir, giving enough flow rate for the motor to produce electricity. This can lead to environmental impacts because of habitat. We have to disturb habitat. It also has changes to the water ecosystems and a great potential displacement for local communities. If we need the land there and there's a community, you gotta buy them out or something like that, get them out of there, put our storage system there. Energy consumption during the pumping phase may still rely on fossil fuels, which is kind of counterproductive to what we're doing, but there's more positives than negatives in this case. There's also limited operational flexibility in areas that are arid. So an example would be like Arizona, there's like deserts, stuff like that. Not enough access to the water that we need.
Okay, so let's try get a understanding of the system's operation. So in terms of our reservoirs, we have our lower and upper reservoirs here. We're planning on using 10-liter containers in cuboid shape. And so we have the measurements here, roughly 20 centimeters on each axis. And what we're going to do is we're going to connect these using piping, like probably PVC piping, but we'll see about that. And the piping is going to be connected to flow control valves, and these are going to help us manage the flow of water between the reservoirs, right? So we have our channels here. We have our discharge channel for the upper reservoir. We also have a charging channel. The reason we have two channels attached to the same reservoir is when we are charging the system up with water, so when we're receiving, we're simulating a reception of energy from the grid during low demand periods. We get power to the pump, basically, from the motor. We pump water up from the lower reservoir. And then we have our flow control valve closed off at the top. And so that's gonna force water to get here. It's not gonna be able to flow past, and so we're gonna have to go up and pump at the top of the reservoir. And we're just doing that to avoid having too much back pressure down here at the bottom of the reservoir if we were to try and pump water through that flow control valve. So that's the reason for having two channels there. And then that would be for the charging mode, and for the discharging mode, water will be flowing down this way. And we will basically have this flow control valve open, and this is open as well. And water is going to flow down past our turbine here. We're planning on using a Francis turbine for the system because that allows us to use the same turbine for pumping and for, I guess, discharging. So planning on using a Francis turbine, attach that to our motor / generator, and yeah, water's gonna flow past here, rotate our turbine. We're gonna generate mechanical energy from that. The generator is gonna convert that to electrical energy that we will supply to the grid during times of high demand. And we're simulating that. Once the water's done its job, it's gonna flow down into the lower reservoir here. And yeah, both reservoirs are the same size, obviously. And yeah, we'll essentially cycle. We sometimes will have open and closed cycles where we can simulate open and closed cycles. I believe this system would be simulating a closed cycle because we're not relying on any natural sort of water sources for this. This is all artificial water sources. So this would be a closed cycle system. Additionally, we also have level sensors in both reservoirs. Obviously, those are going to allow us to determine what level the water is in each reservoir depending on the pumping modes or the charging or discharging mode. And so we're going to use those also to maybe determine pressures, but we'll see about that. The sensors are also going to allow us to basically toggle between charging and pumping modes, depending on where the water reaches in the lower reservoir. So let's say the sensor is at the top of this reservoir. That means that lower reservoir is full. Then we can, if we're simulating a reception of surplus energy from the grid, we know that our reservoir has water to be pumped right up to the top reservoir. And if the upper reservoir is empty as well, then we can confirm, maybe using AntLogic, we can confirm that both reservoirs are ready for receiving water. And that might also allow us to do perform some safety checks, like depending on if this is like full and we're still trying to like put more water in, then obviously we're not going to do that if the sensor tells us that it's full. And yeah.
Alright, moving on to the math portion of our project, we're going to be using potential energy as the max energy we can create throughout our pump system. So we're going to be using the PE formula, with M being mass, G being gravity, H being the height difference in between reservoirs. So we can see that we're going to be using 10-liter buckets, and doing some quick math, we can do 10 liters is equal to 1 liter is equal to 1 kilogram. So we're getting out 10 kilograms for our mass, and then gravity is 9.81, and then we also have our height, which will be a 1 meter difference. So punching that all into our formula, we're getting 98.1 joules. Alright, moving on to our power inputs and output capacity, we're going to be using the formula P equals our efficiency times our PD, which we previously calculated, divided by our time. So on such a small scale project, we're going to have a lot more losses in our efficiency. So we're targeting for like around 50% efficiency throughout our pump system. And obviously we previously calculated our PE. So for time, we have 10 seconds, roughly 10 seconds to 30 seconds to discharge it all from the top reservoir, and then to recharge that top reservoir, we're looking at 60 to 20 seconds. So discharging, we're gonna get around 1.635 watts to 4.905 watts in a power output, and then now charging it, we're gonna put energy back into the system. So with 60 to 120 seconds, we're looking at 408 milliwatts to 817 milliwatts. Moving on to voltages, currents, and conductor sizes of our system. Our system can rely on either 12 or 24 volts. So we're first going to look at charging the system. That will bring us out to a 17 milliamp or 34 milliamp on a 24 volt system. And for a 12 volt system, we're looking at 34 milliamp to 68 milliamp. Now just discharging the system, we're looking at 68 milliamp to 204 milliamp on a 24 volt system. Then on a 12 volt system, we are looking at 136 milliamps to 408 milliamps. We'll be using a 14 gauge conductor size and a 250 milliamp fuse for our safety.
Alright, so the parts we're going to need for our system. We're going to start off with a 12 to 24 volt DC motor / generator. That'll be connected to both sides of the tank via PVC piping. We need a motor / generator because we have 2 modes of operation in our system. During the charging mode is when it will be in the motor mode, because we need to push the water up the system to get up to the upper reservoir to replenish the upper reservoir. And during the discharging stage, it will be in the generator operation, where a turbine will be turned from the rushing water, which will create potential energy. The turbine that we were planning on attaching to the generator is called a Francis turbine, because that turbine is able to do both operations, like the motor and the generator. There will also be a 12 volt battery connected to the motor to simulate the surplus energy coming in from the grid to power the motor to pump the water back up the system. We're also going to have a PLC that's controlling the system, that operates the system, but it's not powered by the system. It's going to have its own separate power supply. We're also going to have a watt meter connected at the end of the system to display the power output of the system. The power out is good just to know A, how well our system works, and B, how efficient our system works, because to calculate efficiency, we would do the power out divided by the power in times by 100. Well, we know we're going to have the water tanks, the upper and lower reservoirs. We're going to use about 10 liter tanks for those. We think that's about the size of a Home Depot bucket. We're thinking about using a Home Depot bucket, but we still haven't finalized any of that yet. Attached to the water tank is going to be a cone-shaped funnel where the water is going to leave the reservoirs. It's just to help to connect it to the flow control. Also attached to the reservoirs is the water control valve, which controls the flow to and from the reservoirs. It just helps make sure that the operation is done correctly without any overflowing or any other water interfering with the actual operation of the system. Inside the reservoirs, we're gonna have water level sensors, which are just there to make sure we don't overflow any of the tanks in either way, and make sure we keep the system running in a smooth manner. Okay, so the way we're gonna connect the PVC piping to the reservoirs is we're gonna have water pipe fittings. We're not sure the material we're gonna use for these yet. It depends on our final specifications, but we will be having watertight fittings to prevent leakage. We're also gonna have the PVC piping, which is to connect both of the reservoirs, like we've been saying. It must be able to withstand the charge and discharge pressure of the water. That's really the only specification we have for that. To connect the PVC to the pipings and everything else, or to the fittings, we're gonna need a PVC glue or the PVC tape that we can use. And that will also be used when we're attaching the PVC piping to the turbine as well. Obviously we're gonna have water in the system, which is gonna be used as the flow to create power, and is also gonna be used as our storage medium to store power. We're gonna have an enclosure for the PLC just to keep that separate and to keep the high power away from everything. And then we're gonna have cabling to connect all the electrical in the system, and then our whole system will be on a trolley with wheels, just so it's easy movement and easy mobility for the jetties.
Alright, moving on to flow rate. So we'll be measuring it by Q equals our volume per second, and in our case we'll do liters per second. Now we're gonna assume that to charge the top reservoir, it's gonna take 1 to 2 minutes, and then to decharge it, it's gonna be roughly 10 to 30 seconds. And then we're gonna use a pipe diameter of roughly 1 centimeter to 2 centimeters. So we have our volume, which is 10 liters. Our time for decharging the upper reservoir is gonna be 10 to 30 seconds, and then to recharge that reservoir at the top, it'll be 60 to 120 seconds. So from those numbers, we're gonna come up with Q of 83.3 milliliters per second, all the way up to 166.7 milliliters per second. That will be for your charging. And then Q of discharging will be 333 milliliters per second, all the way to 1 liter per second.
Thanks for taking the time to listen to our pumped water storage device design review.